quiz 2 is this Wednesday. And remember that the quizzes are not calculations or anything like that. It's just short answer questions about the lectures. So to get ready for those, just skim back through your notes. Try to make a mental note of the key things that are brought up, you know. And then exam 2 is next Wednesday. So that would be the 30th. And then lab exam 2, I think, is the week after that. Well, I'll talk to you about that when we get closer. So the quizzes are the things that are just about the lectures, remembering stuff from lectures. And the exams are the stuff like the problems I assign, you know, so the exams are when you need a calculator and everything is calculations and stuff like that. Anybody have any questions about these? Okay. Well, we haven't had class for a long time. But what we're talking about is, so there's 3 specific types of Newton's laws problems. And for each one of these, but yes?
Oh, I was just kind of confused with your announcement. Was there no labs this week or was it just for the last week?
Just last week. There are labs this week, yes. Okay, so whenever you have one of these 3 specific types, you sort of want to go into that specific approach to this problem. The first one is systems, I guess I call it collections of bodies. With the same acceleration. So an example of that would be like okay, so you have those 2 bodies, and since they're pushing on each other, their motion is going to be the same, their accelerations are going to be the same. And we finished talking about these kind of problems last time. And then there's 2 others, so we're done with this one. And then going on to the second one, this is rolling and sliding problems on inclines. Okay, so so far when we've done rolling and sliding problems, everything has been along a horizontal surface. But what if the surface is at an angle? Okay, so what can we say about these things where there's an angle? And that's the first thing we'll talk about today. And then the third one of these categories is collections of bodies with different accelerations. And these always involve cables and pulleys. Okay. And an example of a problem like this would be say you have a rolling cart here that's attached by a cable to a hanging mass. Okay. And so we're going to finish talking about number 2 today. We'll probably at least get into the start of number 3. Okay. But these are the last 2 things we have to do any kind of Newton's law problem. Okay, so the thing that is weird about this is the first time, I think maybe it's the last time too, that we're going to use sort of a funny coordinate system. So we're going to rotate the coordinate system to match up with the problem. So we'll always rotate the coordinate system so the y-axis points straight out of the surface. So if we have a incline like this, the coordinate system we're going to use is going to have the y-axis pointing directly perpendicular straight out of the surface. And that means that the x-axis has to go like this because these are always rotated versions of the coordinate system we're used to. And so the first question is, why are we going to do this? It seems like a hassle. It's important to remember that this is a choice we're making to make this problem simpler. There's no reason you have to do this, but let me talk about the benefits and the drawbacks of doing this so you can see why this is a reasonable choice to make. So why do we use a rotated coordinate system? So I'll put the benefits over here and the drawbacks over here. Okay, so first think about the acceleration. Remember, like in almost every problem, maybe every problem, we have to think about whether the acceleration is along the x-axis or the y-axis, right? Well, if we didn't use a rotated coordinate system, this would be along something that's not along the x-axis or the y-axis, right? We'd have to use cosine and sine with angles. It would be a pain. But with this coordinate system, notice that all the rolling or sliding happens along the x-axis. Okay, so with this rotated coordinate system, the first benefit is that the acceleration vector is just going to be represented as a0 instead of having a cosine and sine mixed in there. The second benefit is the normal force. So that's the pushing force from the ground. That also, if we used the usual coordinate system, we'd have to use cosine and sine to represent that because the normal force is perpendicular to the surface. But with this rotated coordinate system, this is always just going to be 0n. It's always going to be in the direction of our positive y-axis. And then the third one is the friction force. Now, which way this friction force goes depends on which way the thing is moving. Remember, the friction is always opposite the velocity. But It is always going to be along the x-axis. We just don't know whether it's positive or negative. So I'm going to write this as plus or minus mu times the normal, and then 0 for y. So all three of those would have been more complicated if I'd used a non-rotated coordinate system. There is one drawback though, and it's kind of a pain. There's one thing that's always been easy for us in the past. The weight force has always just been in our negative y direction. But now, remember that weight force is just going straight down. And so notice that a vector straight down isn't along our y-axis anymore. It varies from the y-axis, the negative y-axis, by whatever the angle of this ramp is. So now the weight is going to be represented as mg times the cosine of some angle phi and mg times the sine of some angle phi. So that's definitely gotten considerably messier looking. That's the one drawback. And we just have to get used to representing the weight force in this new rotated coordinate system. Okay. One thing I want you to notice is that that angle phi always varies from 270 degrees by the angle the ramp makes with the horizontal. Okay, so let me show you how this works. So what's this angle phi that we're going to use with the cosine and sine for the weight forces? So first, let's think of a ramp like this. Let's say this angle is 10 degrees. And then for part B, let's say this angle is 30 degrees. And let's give these masses too. Let's say this one's 2 kilograms. This one's 40 kilograms. Okay. Well, the way this works, I'm going to always choose a coordinate system with the y-axis coming straight out of the surface. So for part A, this is my coordinate system. And for part B, this is my coordinate system. And in all cases, all we're doing, I mean, it's just like those assigned problems that you did in the set of vectors problems, you know, where you have a coordinate system at some angle and you're trying to figure out the components of the vector. So for part A, here's our coordinate system. Here's our weight force. And it has a magnitude of 2 times 9.81, so 19.62. And that angle that we need for the cosine and sine is the angle that goes from the positive x-axis counterclockwise until it hits the vector. So there's the angle that we want. Okay. And I said it's always going to be, so it's always going to be 270 either plus or minus the angle that the ramp makes with the horizontal. So in this case, is this 270 plus 10 or 270 minus 10? Plus, yep. Like notice that to get to the vector from the x-axis, you get to 90, 180, 270, and then you have to go 10 degrees farther. So in this case, that phi is 280 degrees. And so the weight force then is 19.62 times the cosine of 280, 19.62 times the sine of 280, and so for a weight force vector here, you get 3.41 negative 19.32. And does this set of components make sense for this coordinate system? Yeah, if you think about the quadrants, it does. Notice that we're in the fourth quadrant of this rotated coordinate system, so we should have a positive x component and a negative y component, and we do. And now let's do the same thing for part B. So this time our coordinate system is this. Okay. And so the angle that we want starts at the x-axis, goes around to the vector. So in this case, is it 270 plus 30 or 270 minus 30? Minus, because we haven't made it to the negative y-axis this time. Okay, so phi is equal to 240. And so we have 392.4 times the cosine of 240. 392.4 times the sine of 240. And I got negative 196.2 for x and negative 339.83 for y. Does it make sense that we have two negative components? Yeah, because in this rotated coordinate system, we're in the third quadrant. Okay, so that's how you find the angles and find the components of the weight force vector. So now all we have to do is just put that into a full problem. So let's start with one where we have a 20-degree angle between the ramp and the horizontal. Let's say that this mass is 10 kilograms. And we want to know what the acceleration vector of the cart is. Okay, we're going to use a coordinate system with the y-axis pointing out. And so the x-axis is this way. And so I'll start with a free body diagram. Okay, we have a weight force down. That's 10 times 9.81, so 98.1. We have a pushing force. The only other place where there's contact with the surroundings at the boundary is at the wheels. That's a pushing force, so that's perpendicular to the surface toward the chosen body. And I'll call that N. Any questions about that? And then let's figure out the weight force components. So our coordinate system is like that. Our weight force is straight down. So what's this angle from the x-axis to the weight force vector? You go, that's the right idea, but you get to 270 and then you go past it another 20 degrees, so it's 290. Okay, so this angle is 290. And so the weight force is 98.1 times the cosine of 290. 98.1 times the sine of 290. And so we get a weight force of 33.55 for X, negative 92.18 for Y. Do those signs make sense? Yeah, it's in the fourth quadrant. So we have a positive X and a negative Y. And now I'll go to Newton's second law. We have the weight force, and that's what we just figured out. Then we have the normal force that's in the positive y direction. And all this is equal to the mass times the acceleration. Is this thing moving along the x-axis or the y-axis? X. So I'll write this as A0. And now we're just trying to come up with the acceleration vector. That just means finding this A and plugging it into this vector. So the X equation here says 33.55 is equal to 10A. So A is equal to 3.36, if I round it, meters per second squared. The acceleration vector is A0, so the acceleration vector is 3.360. Or if you want to visualize that direction, it's in this positive x direction down the ramp with a magnitude of 3.36. Any questions about that? Okay, I have one question. Is this speeding up or slowing down? It's a trick question. So don't answer if you're going to get furious when I trick you.
You don't know.
Correct. We do not know. Exactly. The reason we don't know is because I didn't tell you going into this problem whether the thing is currently moving up the ramp or moving down the ramp. No matter which one of those it's doing, this is its acceleration. But if somebody had given this a shove up the ramp, you know, then it would be slowing down with an acceleration magnitude of 3.36. If it had been just rolling down the ramp, getting faster and faster, the velocity and acceleration would be both in the same direction. It would be speeding up with a magnitude of 3.36. So unless you're told what direction it's moving beforehand, you can't tell whether it's speeding up or slowing down. On friction problems, you always can tell, because I always have to tell you which direction it's rolling in order to do the friction calculation. Okay. Okay, let's do another one. So this time, let's say we have an angle of 25 degrees. And a block with a mass of 2 kilograms. And the coefficient of friction between the block and the ramp is 0.1. And we want to calculate the acceleration vector again. So I'll start with a free body. Oh, and well, I didn't give you the thing I just said I need to give you. For a friction problem like this, I have to tell you which direction it's moving. So let's say that at this instant, it's moving down the ramp. So that's the direction of the velocity. So free body diagram. We have a weight force down. So that's 2 times 9.81, so 19.62. And then the only other place where there's contact is at the ramp. And that takes place in 2 parts. There's a pushing contact from the ground. And then there's a friction force in the opposite direction of the velocity. So this way. And that friction force is the coefficient times whatever that normal force is going to end up being. Any questions about that? Okay, so here's the coordinate system. The magnitude of this is 19.62. So what's this angle that we need for the weight force? Yeah, 245. Yeah. So really all you have to do to know whether you're adding or subtracting from 270 is just figure out whether you're short of, when you get to the vector, are you short of that 270 line or have you gone past that 270 line? Okay. If you've gone past it, you're adding. If you're short of it, then you're subtracting. And so we have 19.62 times the cosine of 245, 19.62 times the sine of 245. and you get negative 8.29, negative 17.78. Does that make sense with the picture, the signs of those? Yeah, we're in the third quadrant. And now the acceleration. Well, in rolling and sliding problems, you're always just going to write that as A0. So that's what I'm going to do here. So the acceleration is A0. It's moving along the x-axis. And now I'll go to Newton's second law. So we have the weight force, negative 8.29, negative 17.78. And then we have the normal force, that's 0n. With the friction force, remember, you have to figure out which direction it's acting. That has to be entered into this equation. We can see from the free body diagram that this is acting in the positive x direction. So I'm going to write this as positive 0.1 n 0. And this is equal to the mass, 2, times the acceleration, a0. We are still just trying to find this a. So you might think we could just go only use the x equation. But with these friction problems, you have to first use the y equation to calculate n and then plug that into the x equation. So the y equation says negative 17.78 plus n is equal to 0. So n is equal to 17.78. And now we'll plug that into the x equation. So negative 8.29 plus 0.1 times what we just got for n, 17.78. Is equal to 2a. And so we got negative 8.29 plus 1.78 is equal to 2a. And we get that a is equal to negative 3.26 meters per second squared. Well, our a vector is a0, our acceleration vector. And so our acceleration vector is negative 3.260. Or it's in the negative x direction. So that means down the ramp in this case. So 3.26 meters per second squared that way. So is this one speeding up or slowing down? Speeding up because it's accelerating in the same direction as its velocity. Yes?
On exams where we're doing this problem, do you want both the acceleration vector?
No, just one or the other is fine. Any other questions? Okay. Let's combine this with the thing that we did last time. So let's say we have a ramp that's at an angle of 5 degrees. And let's say we have a cart here. And it's connected by a cable to another cart. Let's say the first one is 3 kilograms and this one's 5 kilograms. And we're applying a force of 3 newtons up the ramp. And let's say we want to calculate two things. We want to calculate the acceleration vector. And then we also want to calculate the tension in that cable between the two carts. Okay, so for these, so what this is it's a rolling and sliding problem on an incline, but it's also a collection of bodies with the same acceleration. Okay, so for collections of bodies with the same acceleration, what's the first thing that we isolate as a chosen body? The whole thing, yep, exactly. So we're going to isolate the whole thing first to calculate the acceleration, and then we'll go and isolate the individual ones. So free body diagram of the whole thing. We have a weight force down of 8 times 9.81. So that's 78.48, is that right? And then we have this 5 Newton force. And then we have contact with the wheels. There's no friction here. And so this is just a pushing force from the ground onto the wheels. And I'll call it N. If you keep going around the boundary, there's nowhere else that contacts, no other surroundings that contact the boundary, so this is it. Okay. Now let's figure out the components of the weight force. It has a magnitude of 78.48. Is this angle going to be 265 or 275? 275, yep, because you have to go past that negative y axis. So we have 78.48 times the cosine and sine of 275 degrees. So that is 6.84 negative 78.18. Do those components make sense? Yep, it's in the fourth quadrant. The acceleration vector is just going to be along the x-axis, so I'll call it A0. And now put all this stuff into Newton's second law. So we have the weight force, 6.84, negative 78.18. And then that 5 is in the negative x direction, so negative 5, 0. The n is in the positive y like always. And then this is equal to the total mass, 8 kilograms, times the acceleration, a0. The x equation says 6.84 minus 5 is equal to 8a. So a is equal to positive 0.23 meters per second squared. And so the acceleration vector is 0.230. Bless you. Oh. Okay, that's in the positive x direction, which is down the ramp. So you could also think of this as a acceleration like this, down the ramp. All right, we also want to calculate the tension in that cable. You know, presumably, like, we want to figure out how strong of a cable we need to connect these two things, you know, is the reason we would want to know something like that. So now we can isolate either one of these two bodies. It doesn't matter which one. And we're going to use the acceleration we just figured out. I guess I'll isolate the 5 kilogram. So we have a weight force of 49.05. And a pushing force from the ground. That's not the same N as we had before, because the other one included all the pushing forces on all the wheels. So I'm just going to call this N5 just to be extra careful about that kind of thing. And so we got the weight, we got the pushing force from the ground. The only thing we have left is the cable. And so that is away from the body, parallel to the cable, and I'll call it T. We can use the same angle we did for the whole body. You know, the ramp hasn't changed or anything. We're still using the same coordinate system. So the weight force is 49.05 times the cosine and sine of 275 degrees. So that is 4.27 negative 48.86. And now Newton's second law, put in the weight force. this T, this tension force is in the negative x direction. So I'll put this in as negative T0. The normal force is 0, N5. And all this is equal to the mass, which is 5 this time, times the acceleration, which we calculated in part A. So that's 0.230. We're trying to calculate this T. So the x equation says 4.27 minus T is equal to 1.15, and so T is equal to 3.12 newtons. A lot of times I go through like the effort of giving the force as a vector, making sure I have the direction right, you know. I didn't do that here because this problem only asked for the tension in the cable. So that's just the value of that number. Okay, but if I had asked for the force vector that the cable applies to, say, the 3 kilogram cart, then I'd have to go through the thinking after this to say, okay, it's acting this direction and that's this vector. Okay. I think I've brought this kind of stuff up before, but I think at first it's not super clear how this works. Like when we isolated this second body, obviously like the tension in the cable is largely determined by what that applied force is, you know, that 3 Newton force. So how is it that we can, in this second body, I didn't have that 3 Newton force anywhere in my free body diagram, and yet somehow it knows what this tension is? It sort of seems like magic, I think, at first when you see it. But remember that the reason that it works is we already did a step before this where we used that stupid dummy. Did I use multiple numbers at different times? I think I just always used 5, so just change this to 5. Okay, but so when I isolated everything together, we calculated that acceleration based on the fact that there was that 5 Newton force there. Okay, once we calculated that acceleration and used that for part B, that 5 Newton force was already like baked into our acceleration results. So that's why it doesn't need to know that a second time, you know. Okay, I think that's it for that. So let's go on now to collections of bodies with different accelerations. And we're always going to see this, like this can only be problems that involve cables and pulleys. And so, you know, an example of this would be like, you could have a body here on an incline connected by a cable to something like this. And if that hanging mass is big enough, then it's going to accelerate down. But this rolling thing isn't going to accelerate down. If the hanging mass accelerated down, the rolling thing would accelerate up the ramp. So those two things have totally different acceleration vectors. Okay, so that's what's going on here. That's what I'm talking about with them having different accelerations. And the approach that we're going to use is first we're going to isolate one body. First body to isolate. And its acceleration vector will either be A0 or 0A, just depending on whether it's free to move along its X or Y direction. Okay, now for the second step, now we're going to isolate, choose the other body to isolate. But this time, we have to do something with the acceleration that we haven't done yet. So to find the acceleration for this one, imagine moving the first body I say 1 inch. It doesn't really matter how far, but just imagine moving the first body a little bit in its positive direction. So imagine moving the first body 1 inch in its positive direction. That'll tell you how to represent the acceleration of the second body. Okay. Now you have Newton's second law from the first body, Newton's second law from the second body, and you just have a system of equations that you have to solve by substitution. So solve this system of Newton's second law equations. Substitution always works. So let's see how this goes with an example problem. Okay, so let's say we have a rolling object here, and it has a mass of 5 kilograms. And then you have a hanging mass of 1 kilogram. And let's say we want to calculate the acceleration vector and the tension in the cable. Okay, so first, this is a rolling, sliding problem. Do we have to use a funny coordinate system for this or just the regular one? Yeah, notice that when the surface is horizontal, if you follow the rules of rolling and sliding problem coordinate systems, it just gives you the normal coordinate system back with the y-axis pointing straight up. I'm going to start out by isolating the 5 kilogram thing. I usually just work left to right. But it doesn't matter which one you use first. So free body diagram of the 5 kilogram. There's a weight force down of 49.05. There's a pushing force from the ground, N. And then there's a pulling force from the cable away from the body, and I'll call that T. So Newton's second law says 0, negative 49.05. Plus 0n plus T0 is equal to the mass 5. And now, does this thing move along its x-axis or y-axis? X, and so I'll do this as A0. And so I get two equations. The x equation says T is equal to 5a. And the y equation says negative 49.05 plus n is equal to 0. But we can't solve anything yet because that's 3 variables and 2 equations. Okay, so now we have to just go to the second body. Sort of, we're setting these aside for, we can't solve these, so we're just setting them aside. And now I'll go to the hanging mass. There's a weight force of 1 times 9.81. There's a pulling force up from the cable. It's the same cable as before, so this is still T. And now we have to think about the acceleration. So the acceleration for this one. So what we're going to do is we're going to think about moving the first body an inch in its positive direction and think about where the other one would go. Okay? If we rolled this cart 1 inch to the right in the positive x direction, where would this one go? It would go down, and it would go down 1 inch, and so we know that the magnitudes of the accelerations are going to be the same because they go the same distance. But now we're going to write it as 0, negative a. So this is what we got from moving the first body in its positive direction. And now Newton's second law. says 0t plus 0, negative 9.81 is equal to the mass times the acceleration of 0, negative a. And so we get two equations here. The x equation is totally useless in this case, but the y equation gives us some stuff. So t minus 9.81 is equal to negative a. Well, we're just trying to find a and t. So I'm going to use this equation and this equation. Solve them by substitution. So I'm going to solve the two circled equations. So this first one says t is equal to 5a, so I'll just plug that in for t. So negative 9.81 is equal to negative 6a. And so a is equal to 1.635 meters per second squared. You can see whichever one of these two bodies you look at, that's saying that the rolling one is moving in the positive x direction. The hanging one is accelerating in the negative y direction. So the whole thing is like, the hanging mass is going down. And now to calculate t, you can go to any equation you have, as long as you haven't made any mistakes, is valid. So just look for one that'll give you t. We know that t is equal to 5a. So 5 times 1.635. So the tension in those cables is 8.18 newtons. Any questions about that?
Just a question on after the acceleration vector.
Oh, yeah.
So are we supposed to keep that?
Right, I guess I didn't say which one of those two. Let's say we want the acceleration vector of the 5, just so we have one or the other to figure out, okay? So now go back to what we know about the 5, and we decided that the acceleration vector for the 5 was a0. And so now you can just plug it in there. So this tells us that the acceleration vector for the 5 is 1.635. Or in other words, it's going this way at 1.635. Any questions about that? Let's do one more quick one. So let's say this time we have a pulley hanging from the ceiling. And we have a 3 kilogram mass on this side. And a 4 kilogram mass on this side. And we want to calculate the acceleration vector of the 4 kilogram. Well, you can see from just looking at this system that the 4 is going to be accelerating down, the 3 is going to be accelerating up, right? So we know when we get our answer, that's what it should say. I'm going to start by isolating the 4 kilogram. We have a weight of 39.24 and a pulling force up of T. And is the 4 kilogram moving along the X or Y axis? Y, so our acceleration vector is just 0a. Newton's second law says 0t plus 0, negative 39.24 is equal to 4 times 0a. Well, you can see the X equation doesn't give us anything. It just says 0 equals 0. The Y equation says T minus 39.24 is equal to 4a. We know we're not coming back for that 0 equals 0, but this one we're going to come back to. But we have to come back to it because there's 2 variables in one equation. So there's nothing you can do to solve it. So now we'll go to the 3 kilogram. The weight is 29.43. It's the same cable, so there's still a tension T pulling up. If the 4 kilogram, so now go back to your first chosen body, and that was the 4 kilogram. And now think of it moving an inch in its positive direction. And notice that's not the direction this system is going to be moving. But normally you don't know that right off the bat. So you just have to sort of follow the steps. Okay, so if the 4 kilogram moved an inch up, which way would the 3 kilogram move? Yep, an inch down. And so the acceleration vector here is 0, negative a. And now we'll go to Newton's second law. We have 0t plus 0, negative 29.43 is equal to 3 times 0, negative a. Again, the X equation doesn't give us anything. But the Y equation says T minus 29.43 is equal to negative 3a. And so now we're going to solve these 2 circled equations by substitution. I guess I'll say from this one, I'll rewrite this as T is equal to 4a plus 39.24. And then I'm going to put that in place of the T here. So we got 4a plus 39.24 minus 29.43 is equal to negative 3a. And so we have positive 9.81 is equal to 7a. So a is equal to negative 7a, thank you. So a is equal to negative 1.40 meters per second squared. And now from our first body, we're trying to calculate the acceleration of the first one we chose. Our a is 0, our acceleration vector is 0a. So now just plug a in for there, and we get that the acceleration vector of the 4 is 0, negative 1.40. Or down at 1.40. So even though we didn't ever have to make the assumption that the 4 was accelerating down, it all worked out in the math and told us what happens. Okay. All right, let's stop there. Yeah, there's a lab this week, but it's shortish and should be pretty straightforward, I think. Yeah.